Okay, in this video we are going to find a definite integral by taking the limit of a Riemann sum, and specifically we're going to deal with a linear function, so it'll be the integral from 0 to 2 of the quantity x plus 5 dx. So let's get started. So to evaluate these, you need to basically find two things and then remember how to do it. So the first thing we need to find is delta x. And delta x is, in general, b minus a over n, where b is the kind of ending value for your definite integral, and a is the starting value. So in this case, it's going to be 2 minus 0 over n, which reduces to 2 over n. Okay, so we found delta x. We also need to find x sub I, which I call an evaluation point. And an evaluation point is where you're starting, so that's a, or 0 in this case, plus I times delta x. So it's going to be 0 plus I times delta x, but we found delta x was 2 over n. So we're going to write this as it's 0 plus 2i over n, but let's just write 2i over n. And we're pretty much good to go. So our definite integral is this. It's going to be equal to the limit as n approaches infinity of, and now we need to think about what we're doing. So in general, we're making a lot of rectangles and adding them up. And the area of a rectangle is base times height. So it's actually going to be the sum of, because we're adding them up, so from 1 to n, so from the first rectangle to the last rectangle that we deal with. And then the, the height is just going to be f of our evaluation points, so f of x sub I. And then the base is going to be delta x. So that's what we want to evaluate, so let's evaluate it. So we get this limit, so we go to infinity. Alright, so now we need to deal with f of x sub I. So f of x is the integrand, so it's x plus 5. And x sub I is 2i over n. So every x that we see in the integrand, we're going to replace with 2i over n. So that's going to give me 2i over n plus 5. And then we need to multiply by delta x. So 2 over n. And now it's just a lot of arithmetic and remembering a couple of rules. So we'll get this, still a limit. I'm just going to distribute the delta x in this case, so I end up with 4i over n squared plus 10 over n. And so one of the rules is you can basically distribute the summation, and you can factor out anything that doesn't involve I. So for example, the sum of 4i over n squared, I can take out 4 over n squared, because those are not dependent upon I. And then when I get to 10 over n, the sum of 10 over n, I can actually factor out 10 over n and just have the sum of 1. So I'm actually going to do that. So we still have our limit. So I'm taking out 4 over n squared. That leaves me with just the sum of I. And then I'm going to take out 10 over n, and that'll leave me with just the sum of 1. And now we need to have some formulas memorized. So let's start by writing what we know. So 4 over n squared is just going to stay. And then if I look at the sum of I have memorized that the sum of I from 1 to n is n times n plus 1 all over 2. So you definitely need to memorize those if you're going to go through this process. So we have that, plus we got our 10 over n. And then I've also got memorized the sum from 1 to n of 1 is just n. So we have this, and close our parenthesis. And now we need to take the limit as n approaches infinity. So you could like expand numerators, divide through by the highest power in the denominator, and then look at it that way. It's easier to look at these as rational functions, and you're finding the horizontal asymptote. So I look at this and I see this is second degree. The numerator, if I expand it, is also second degree. So to take the limit, I just need the ratio of the coefficients, the leading coefficients, which are 4 and 2. So that's going to give me 4 over 2. And then you could kind of do the same thing on this 10 over n times n, although, I mean, the n's just cancel there, but it's a first degree and a first degree. You'll find if you do enough of these that if the degrees don't match, you know, the degree of the denominator and of the numerator, then you probably did something wrong. Actually, I think you definitely did something wrong if they don't match. So we get this, and if you add those up, you get 12. So what we just figured out was the value of the definite integral from 0 to 2 of x plus 5 is 12. Alright, so I hope you found this helpful. That's just an example of how you can run through this, and good luck.